We are talking about categorical data analysis, and you'll recall that when we were looking at a quantitative response variable in which we had multiple categories, when we rejected the omnibus null hypothesis, we wanted to cue in on specific differences to see if in fact we could infer not just a general omnibus hypothesis, but infer something about specific comparisons. And there are multiple comparisons that we can make. The same is true when we have a categorical response variable. Multiple comparisons are used to compare two categories or clusters of categories. Now we could do pairwise comparisons in which we compare one proportion to another. We can do complex comparisons in which we combine these comparisons together for a couple groups or more than two groups and compare it to one or more than two groups. That is one way we can classify comparisons, but we can also classify them on the basis of whether we're doing it after the omnibus analysis, in which we call it post hoc, or if we're going to skip the omnibus analysis and plan in advance what comparisons we're interested in and do these a priori or planned comparisons. In terms of the methods that we can use, when we were looking in a previous video series at a quantitative response, we looked at three different methods: Tukey, Bonferroni, and Scheffé. Tukey is when we did all pairwise comparisons, but it is only available for all pairwise comparisons of means, and we're looking at proportions. So Tukey is no longer with us. It is off the table here. The other two, however, remain. The Bonferroni method is a very general method that can be used for any kind of multiple comparison because all you're doing is adjusting the type 1 error rate. You're just adjusting your alpha and using an alpha or adjusted alpha for each of your comparisons. So Bonferroni is available here when we're looking at comparisons of proportions, just like when we were looking at comparison of means. We don't actually have a true Scheffé when we're comparing to proportions, but we have a Scheffé-like method. And it works like Scheffé in that you can use it for fishing expeditions. You can look at the data. You can do the omnibus test first. You can look for big differences and say, I want to hone in on those. It also works the same in that you calculate a single critical value, no matter how many comparisons you're doing, and you can use that critical value for all comparisons. Whereas, remember, with Bonferroni, if you have a certain number of comparisons, you're going to have a different critical value than if you have a different number of comparisons. Now, what are we actually comparing here? We're comparing proportions. We're looking at the population proportions and using the sample data and sample proportions to see if we can make inferences about population proportion contrast. So psi, our contrast here, is equal to a proportion in one condition minus a proportion in another condition for pairwise, but for complex, psi could be a combination of proportions in conditions contrasted with a third. Why might we want to do that? Think about our teacher example. Perhaps we want to compare those who had any amount of training to those who did not. In that case, we would combine some and much training and contrast it with no training. So there are logical reasons for wanting to do complex instead of pairwise comparisons, even though pairwise comparisons remain the most popular type of comparison for obvious reasons, because you're drilling down as specifically as you can in order to look at contrasts among pairs. What statistics do we need when we're comparing contrast? Well, first, a contrast is simply a sum of weighted proportions. In the case of the pairwise contrast that we see back here, you can think of a 1 and a minus 1 being in front of pi 1, 1 and pi 1, 2 respectively, and then you add those together. So you're adding up 1 times pi 1, 1 plus negative 1 times pi 1, 2. That's what I'm looking at in this first formula here. I'm summing up a weight times the proportion, so 1 times pi 1, 1, plus minus 1 times pi 1, 2, and that gives me my pairwise proportion. Similarly for complex, notice the half's actually written in there, so I have half times pi 2, 1 plus half times pi 2, 2 plus negative 1 times pi 2, 3. So in general, a contrast is simply a weighted sum of proportions. The estimate of the contrast is, no surprise, a weighted sum of the estimates of the proportions. We don't actually have the population proportions, but we have the sample proportions, so we simply use a weighted sum of those sample proportions, and that gives us our contrast estimate. What else do we need in order to construct a confidence interval? We need a standard error of our estimate, and we need a critical value so that we can take the product of the standard error and the critical value to get a margin of error. The standard error of a contrast estimate, this looks like a scary formula, but it's not too bad, and you'll see it in action when I do an example. We're taking the proportion times 1 minus the proportion, dividing it by the number that went into calculating that proportion. That should sound familiar. When we were taking a standard error of a mean, we took the mean, divided by the number that went into calculating that mean, and we also multiplied it by the square of the weights. If you're doing a pairwise contrast, the weights are 1 and minus 1, so you're just using as weights 1 and 1, because the square of 1 and the square of minus 1 are both 1. And so we would just simply sum up a proportion times 1 minus the proportion. Well, think about 1 minus the proportion, what that is. If we're looking at the proportion that are punitive in the no teacher training group, 1 minus that proportion would be those that are not punitive, those that fit into one of the other categories of either reasoned or evasive. So you're taking proportion in the category you're focusing on times everyone else, times the proportion that are not in that category. And if you recall from your Stats 101 course, your first statistics course, when you actually looked at a difference of proportions, you looked at pi hat times 1 minus pi hat, or p hat times 1 minus p hat. That's the same thing we're doing here. And you also divide it there by n. Here we're dividing by n for the group, but now we have more than 2 groups, so we're dividing by n of whatever group we're focusing on when we look at that proportion. You take the sum of these weighted proportion times 1 minus proportion over n's, and you take the square root for the standard error. If you don't take the square root, you have the variance of that contrast. Take the square root for the standard error. Now we need the critical value. And for a critical value, which if we're doing post hoc, we're going to use a Chaffee-like. Notice the S with a star. That means Chaffee, and the star means not quite. It's like Chaffee. This is used after rejecting an omnibus hypothesis. You can look for the differences that look interesting to you, such as the largest differences, and it controls the type 1 error rate for all comparisons. So it's a true post hoc method. And the Chaffee type critical value is simply the square root of the critical value that you use for the omnibus test. So if you can calculate the critical value for the omnibus test on a chi-square distribution with nu degrees of freedom, that's what that Greek letter here is nu. It just stands for the degrees of freedom at whatever confidence level you're interested in. If you can find that critical value and take the square root, you've got it. You've got the critical value for Chaffee. We multiply that by the standard error, and that gives us our margin of error. If we're going to do an a priori or planned comparison, that means we're not going to do the omnibus test. We're going to decide ahead of time what contrast we're going to do. And by deciding ahead of time what contrast we're going to do, we know how many of them there are. So you're purposefully controlling the type 1 error rate by dividing it up. That Bonferroni critical value is calculated using the normal distribution, which is the same distribution that we used back in Stats 101 when we compared proportion 1 to proportion 2. We used the normal distribution. So note here that the z is a z statistic from the normal distribution, but instead of using alpha, we use alpha prime, which is just alpha divided by the number of comparisons. So if you're using an alpha for the overall family-wise rate of 0.05 and you have 2 comparisons, you would use alpha prime of 0.025, that is 0.05 divided by 2. And then you calculate your z critical value on a normal distribution using 0.025 total, which means you got to split it by 2 again in order to put 0.025 over 2 or 0.0125 in each tail of the distribution. So that's going through these formulas in words, but of course, learning about formulas always makes a lot more sense when you take it in context with an example, so let's do that now. Here we are looking at our teacher training example. We've already rejected the omnibus null hypothesis up here, so I'm ready to do a post hoc comparison. We've determined the conditions are not all homogeneous with respect to how students are dealt with when they misbehave, that it seems to be related to how much training the teacher had. So to create these post hoc confidence intervals, first thing I might want to do is go back and look at these proportions and see where I see potential differences. So that's way back up here. Well, I notice a couple things stand out to me. The proportion of punitive with no teacher training and the proportion of punitive with much teacher training. That seems to be a big difference. Here's another big difference. The proportion of reasoned with no teacher training and the proportion of much with no teacher training. So coming back down here, I state the following. It seems an obvious difference is the difference in punitive responses for those with no teacher training and those with much teacher training. Now, here is row 1, column 1 for the proportions. And if you look back on there, that's no teacher training, punitive. The next one that I have here is row 1, column 3. And if you look back up here, you probably can guess what it is. It's much teacher training, punitive. Okay, so what I'm doing here is calculating the contrast estimate. Now, that's a contrast, and you can think of it as having a hat on it because this is for a statistic. So looking at the first contrast, we have a 0.33 difference in proportions, or if you're talking about differences in terms of percentages, you would say 33.33 percentage points. Don't say 33.33% difference. That has a different meaning than just taking a differences. When you take a percentage difference, you're talking about taking an original value and multiplying it and then subtracting. We're not doing that. So it's a 33.33 percentage point difference. So looking back up here, we can actually see that. We had 45%, we had 12%. That's a 33 percentage point difference. Now that I have that, we need the standard error. So the formula for standard error says we need to take that proportion we're focusing on in the no teacher training group that was punitive. We have to multiply that by everyone else in no teacher training that was not punitive. And that's 1 minus that proportion. So it's the proportion we're focusing on times 1 minus the proportion that we're focusing on. Once I have the proportion who were punitive in the no teacher training group times those in the no teacher training group, the proportion that were not punitive, I have to divide by the number that went into the punitive proportion in the no teacher training group. And remember, the total in the no teacher training group was 60. 60 were drawn from each of 3 teacher conditions. So that's the 60 there. Then I am comparing that to the proportion in the much training group that were punitive and those in the much training group that were not punitive. And again, the proportion is calculated based upon 60 teachers, this time a different 60 in the much training group, and so I put a 60 there. And that gives me my standard error once I take the square root of that. So there's my standard error of 0.7 about 7, or about 6, 0.76. Now for Chaffee's critical value, remember that I take the critical value for the omnibus test. That is taking a quantile of the chi-square distribution that has 95% of the area beneath it for a 0.05 test, and I had 4 degrees of freedom because I took the number of columns minus 1 times the number of rows minus 1, that's 2 times 2 or 4, and that gives me my critical value for Chaffee. So I can now get my margin of error for this contrast by taking the standard error times the critical value. That gives me my margin of error. And if I add and subtract the margin of error from the contrast, there I have the answer. So what I'm able to infer with 95% confidence is that, let's call this about 0.1. The proportion is 0.1 or 10 percentage points all the way up to about 0.57 or 57 percentage points different for the no teacher training group than for the teacher training group, with the no teacher training group being more punitive. So how many of them are more punitive outside of this sample? What can I infer to the larger population? It could be as little as 10 percentage points more, which is still quite a bit, or it could be as much as 57 percentage points more in the no teacher training group compared to those who had much training. So that gives us more specific information about the no training and much training than the omnibus hypothesis does. Let's look again at punitive responses, but this time compare those with no teacher training to those with teacher training in order to exemplify a complex contrast. So here's the no teacher training group, here is the some teacher training group, and here is the some teacher training group. Notice my weights for some are -half and -half. So the weight for punitive in the no teacher training group is 1, but the other weights are -half and -half. You remember from a previous video that the rule for a contrast is they have to add up to 0, those weights, and they do. They add up to 0 here. So this is a complex contrast. If I then get the standard error of that, I have, again, the proportion punitive and not punitive multiplied together in the no teacher training group, the same with the some teacher training group, the same with the teacher training group. What's different here is instead of a 1 squared, I now have a half squared. What about the minus sign? You don't need it because you're squaring. So I have a half squared for each of the teacher training groups, and I'm dividing again by 60 because there were 60 in each of the teacher training groups. Here again is our MO. Notice I didn't have to calculate a new critical value. Once you calculate it one time for the Chaffee-like critical value, you have it. And now we have our confidence limits here. So this tells us when I'm comparing those with no training to those with an amount of training, whether it's a little or a lot, that I'm 8 percentage points higher of being punitive with the no training group than with any kind of teacher training, up to 52 percentage points more that are punitive in the no teacher training group than those in with any kind of teacher training. So I've definitely clearly found that comparing the no training to much training or comparing the no training to any amount of training gives me more punitive with the no training group. There are many more of these contrasts, obviously, we could do in order to study these teacher training conditions, but I'm going to stop there, having shown you one post hoc comparison that's pairwise, one post hoc that's complex. How would this change if I was doing Bonferroni? it would change back here in terms of the critical value. For the critical value for Bonferroni, instead of taking a chi-square, I would be taking a z-statistic. And that z-statistic would have to be based upon a percentile in which I've adjusted alpha by the number of contrast I'm doing. That's the only thing that would change here, except that we would have to make these comparisons be planned out in advance, and we do these instead of doing the omnibus. So that's an overview of the simple methods for categorical data analysis that we can do. In the next video, I'm going to put everything together using this same example to construct a report based upon analyzing categorical data. So I hope to see you there.